after calculating the z-test statistic, we want to make a decision to either reject the null or fail to reject the null. And there are really two ways of doing this, two main ways. For step 4a, we're going to talk about comparing the test statistic with a critical value, or in some contexts, a set of values. The critical value or values, it's based on whatever we set the significance level alpha to. Right? For a two-sided z-test, where the alternative is that the population mean does not equal that claimed value, right? If the absolute value of our z-test statistic is greater than or equal to z alpha divided by 2, then we're going to reject the null that the population mean is equal to that claimed value of the population mean. For a right-sided z-test, where the alternative is we're just looking at whether or not the population mean is greater than the claimed value. Right? If the z-test statistic is greater than or equal to z alpha, then we reject the null. If we conduct a left-sided z-test, where the alternative is that the population mean is less than the claimed value, mu naught, then if z is less than or equal to negative z alpha, then we're going to reject the null, where z alpha is based on 0.05. So let's look at a two-sided test in which alpha equals 0.05. Right? For a two-sided z-test, right, we're going to use a benchmark of negative 1.96 and positive 1.96. Right? The idea is that if we have a z-test statistic greater than 1.96 or less than negative 1.96, we're going to reject the null hypothesis. Right? Because what we're doing is we're assuming that the null is true. We're saying that if the null is true, the sampling distribution is going to be centered around mu naught. It's going to be centered on that claimed value. And then we're going to see where our z-test statistic lies. Right? So just to be clear, we have these two areas that we call rejection regions. Right? So with a right-sided test, in which alpha equals 0.05, if the z-test statistic is greater than or equal to z alpha, then we're going to reject the null. So with alpha equal to 0.05, that value of z alpha is 1.645. And that area shaded in blue, that area has a probability of 0.05. You know, the probability of having a z-test statistic greater than 1.645 is, that's given by that particular value. Right? For a right-sided test, right, we have this particular rejection region. Okay, our rejection region is only in that part of the sampling distribution model, because we're only interested in whether the population mean is greater than the claimed value. Right? We're not interested in whether it's less than the claimed value under the null hypothesis. For a left-sided test in which alpha equals 0.05, right, our benchmark for comparing our z-test statistic is negative 1.645. Right? That area in green, has a probability of 0.05. That is our rejection region. If our z-test statistic is in that region, right, if it's less than negative 1.645 and we're conducting a left-sided z-test, then we're going to reject the null hypothesis. We're going to reject the null that the sampling distribution is centered on mu naught. So let's look at how we can apply the critical values approach. The basic idea is we calculate a z-test statistic, and then based on whatever we set alpha to, and based on whether or not we have a two-sided left-sided or right-sided z-test, we're going to have critical values by which we compare our z-test statistic. Right? Suppose we calculate the following three z-test statistics: 0.85, 4.92, and negative 1.99. So suppose that we just happen to calculate these z-test statistics. For alpha equal to 0.05, what would we conclude if we conducted a two-sided z-test, a right-sided z-test, and a left-sided z-test? For a two-sided z-test with alpha equal to 0.05 and a z-test statistic of 0.85, right, we're going to reject the null if the absolute value of our z-test statistic is greater than or equal to z alpha divided by 2. Well, z alpha divided by 2 is 1.96. Absolute value of our z-test statistic is 0.85. So in this case, we would in fact fail to reject the null hypothesis. To put another way, our z-test statistic is not that extreme. It's pretty likely to have occurred under the assumption that the null is true. Right? So we can see that here visually. Right? How about a two-sided z-test with z equal to negative 1.99? Well, again, if, in this case, the absolute value of a z-test statistic is greater than or equal to z alpha divided by 2, then we're going to reject the null. Well, in this case, right, the absolute value of negative 1.99 is 1.99. Right? That is greater than 1.96, so we, in fact, reject the null in this case. To put another way, that value of negative 1.99, that z-test statistic, it lies within the rejection region. It's less than negative 1.96. Right? So we're going to reject the null. It's pretty unlikely that we would have obtained the z-test statistic if we think that the null is in fact true. Right? For a right-sided test, and a z-test statistic of 0.85, we're going to reject the null if z is greater than or equal to z alpha. Right? So in this case, the idea behind it is that it's pretty likely that we would have obtained a value of 0.85. Right? For a right-sided test in which we have a z-test statistic of 4.92, okay, we're going to reject the null if our z-test statistic is greater than or equal to z alpha. Right? Z alpha in this case is 1.645 because it's a right-sided test, meaning the alternative is that the population mean is greater than the null value. And so here we have a z-test statistic of 4.92. It's pretty unlikely that we would have obtained the z-test statistic, assuming that the sampling distribution is centered on mu naught. Right? For a right-sided test with a z-test statistic of negative 1.99, you can see that a z-test statistic, right, it's not within the rejection region. Okay? It's, under the construction of this hypothesis, it's likely that we would have obtained this z-test statistic. And that's because our alternative is simply that the population mean is greater than the claimed value of the null hypothesis. For a left-sided test, we're going to look at these z-test statistics again. So for a left-sided test, if the z-test statistic is less than or equal to negative z alpha, then we're going to reject the null. So when we have alpha equal to 0.05, our value of negative z alpha is negative 1.645, meaning the probability of getting a more extreme, a more negative test statistic is 0.05. It's within that green region. Right? So using this critical value to compare our z-test statistic, right, we find that a value of z of 0.85 is pretty likely. Right? So we're going to fail to reject the null hypothesis. It is not more extreme than negative 1.645. For a left-sided test using a z-test statistic of 4.92, again, we're going to fail to reject the null. Right? That's because we're using, for a left-sided test, we're just interested in whether or not the population mean is less than the claimed value of the null. And so when we have a z-test statistic of 4.92, right, in that case, we're not going to reject the null hypothesis. Right? For a left-sided test in which we have a z-test statistic of negative 1.99, you can see that that does lie within the rejection region, meaning with this z-test statistic, right, it's more extreme, it's more negative than negative 1.645. And so we're going to reject the null. Right? That's because for a left-sided test, our alternative is that the population mean is less than the claimed value of the null. So just to put all of this in perspective, you can have a two-sided, a left-sided, or right-sided test. With the critical values approach, what we do is we take our z-test statistic and we compare it to some critical value. And we say, well, using this benchmark, using this critical value, we're going to either reject the null or fail to reject the null. And in general, the more extreme the z-test statistic, the more likely we are to reject the null. But of course, that depends on what we mean by extreme. For a two-sided z-test, extreme means either negative or positive, some large value. For a right-sided test, right, we're only going to be interested in z-test statistics that are extremely positive, whereas with a left-sided test, we're only going to be interested in making conclusions based on z-test statistics that are extremely negative. And with that, we're going to work through a few examples of using critical values and comparing those critical values to our z-test statistics to make a decision about whether we're going to reject the null or fail to reject the null.